Hello, Mr. Mailer here, your online math teacher, and welcome to my channel. Today we're going to be continuing my series on exponential and logarithmic functions, and in particular, we're going to begin talking about logarithmic functions. So we built up a little bit of understanding about exponential functions, so now we can talk about logarithms since we've done that. So if you find today's video helpful, useful, consider annihilating that like button, subscribing, sharing this with your friends or anyone else. So let's get going. So I'm going to begin by defining what a logarithm is. So we are going to define the logarithm in the following way. Let a be a positive number with a not equal to 1. Then the logarithmic function with base a, which we're going to denote by log, so log, a little subscript a, of x. So we're going to define it by log base a of x is equal to y precisely when x is equal to a to the y. So what that means is log base a of x is the value y, so it's the value y, so that when you raise that base of our logarithm to the y power, you're going to get that value of x back. And we have two different forms that you can jump back and forth between when you know this stuff. The first is what I have written on the left up here. The logarithmic form of something is, and I write it as y is equal to log base a of x. And the exponential form for this same statement is that a to the y is equal to x that I have on the right up top. So now make that look like a y instead of 4. So these two different forms encode the same information. It's just how you're denoting it and arranging it. And there's advantages to logarithmic form versus exponential form. But you might be asking yourself, well, okay, I'm seeing this algebra. I guess that I can pick up the difference in this notation, but what really is this function? And to understand this function, I want to look at a graph, because exponential and logarithmic functions are really just inverses of each other. So say I want to know what the graph of log base 2 of x is, then that definition really just defined the inverse of an exponential function. So it turns out that log base 2 of x and 2 to the x are inverses. And more generally, log base a of x and a to the x are inverses. So if I want to understand what the picture looks like, I just need to understand exponentials really well. So I should know how to graph a function like 2 to the x at this point, and it looks like the following. So I got 4 points drawn right here, and then I have my horizontal asymptote at y is equal to 0. When we talk about inverse functions, the way you can get the graph of an inverse function is by reflecting over the line y is equal to x. And that really just means swap the x and y coordinates of points, swap x and y as far as your asymptotes go. So if I want to get log base 2 of x, knowing that this is the graph of 2 to the x, y is equal to 0 as an asymptote, switching x and y becomes x is equal to 0 as an asymptote. So my logarithm is going to have an asymptote at x is equal to 0. My point at -1, 1/2 goes to 1/2, -1. My point at 1, 1, switching x and y, goes to 1, 1. My point at 1, 2, switching x and y, goes to 2, 1. And my point at 2, 4 is going to go to 4, 2. And this is what my general graph looks like for log base 2 of x. So if you're wondering what the picture of logarithms look like, they kind of look like exponential functions, just instead of having a horizontal asymptote, they now have a vertical asymptote because of this reflection over the line y is equal to x. So this is the picture of them. So you really want to think of these two functions as being inverses of each other. Now, logarithms have some nice properties that we can use when we work algebraically. So understand this picture, and then you can work algebraically. And these properties you can think of as coming from our knowledge of exponents. So if we know a to the 0 is going to be equal to 1 for positive a values. So that means log base a of 1 is equal to 0. Because remember, the output is the power in the exponential form. The base in our logarithm is the base here, and what's inside our logarithm is 1 is what we're equal to over here. Similarly, a to the first is equal to a as an exponential form tells us log base a of a is equal to 1 in logarithmic form. Now, 3 and 4, you can think of these properties as coming from inverse functions. So if f and g are inverse functions, this is going to happen if and only if f of g of x is equal to x and g of f of x is equal to x. So whenever you compose inverse functions with each other, you should just get x back out. So since log base a of x and a to the x are inverse functions of each other, this should just give us back out x. Same thing with a to the log base a of x. Since a to the x and log base a of x are inverses, they should just give us back x. And we can use these properties to evaluate some simple things with logarithms. For instance, if I want log base 7 of 1/49th, I know that 1/49th is the same as 7 to the negative second power. So since I can express this as 7 to the negative second power, by this third rule up here, I'm just getting that power back out. So it evaluates to negative 2. If I want 8 to the log base 8 of 32, that's just this rule 4 here. I'm going to just get back out this 32 that's inside. Log base pi of pi, because I never said I have to have integers for my bases of my logarithms. That's the same as looking at property 2 up here. Log base a of a is equal to 1. So log base pi of pi is equal to 1. And then e to the log base e to e to the x, if you want to think of it, there's multiple ways to think, but log base e of e to the x is equal to x. So if we simplify the exponent with property 3, we're just left with e to the x here. So we can use properties of logarithms to evaluate logarithms. Sometimes you might get a function, sometimes you'll get an explicit value. But another thing you want to keep in mind with these problems is notationally we might get something different. So there's some special notation you want to know for logarithms. The first is when we have base 10. And 10 is special because that we work in a base 10 number system. And a base 10 logarithm is going to be called the common logarithm. And we're going to denote this common logarithm by just omitting the base. So instead of writing log base 10 of x, when we're talking about the base 10 logarithm, we usually just write log of x, and we don't write a base there. So if you ever see log written without a base, it's base 10. The other special notation we have is for a logarithm with base e. And because you'll remember, e to the x was a special exponential function, the natural exponential function. So we're going to have a logarithm that's special to go along with base e as well. And this is called the natural logarithm. And we denote the natural logarithm by, instead of writing log base e of x, writing ln of x. You can think of the natural logarithm initials being switched around to give you logarithm natural. Kind of sounds kind of French. Probably isn't. I don't know. Actually, it could be. And you can still use the same properties to evaluate. So log base e of e to the 20th power is just going to give us back out 20, and that's using property 3 up here again. E to the natural log of x plus 1. Again, our properties. This is property 4, so it's just going to give us back out what's inside of that logarithm in the power. So it's going to just leave us with that x plus 1. And while it's not proper to say this, whenever you have a logarithm with a base and an exponential function with that same base, I usually say they're effectively canceling each other out. So that's how I think of these. So ln, that's base e, is going to cancel with that e to leave us with 20. E to the ln, so that's a base, natural logarithm. They'll cancel in a sense to leave you with x plus 1. It's not proper terminology, but that's how I like to explain it. And the last thing I want to talk about here is you might be given some sort of transformation or variant on a logarithm. In this case, you might have something like natural log of 16 minus x squared, and you might want to find the domain of that function. You can use your knowledge of what the graph looks like to help you. And what I mean by that is you can see with our picture here, we are only able to evaluate a logarithm at positive values of x, because at x is equal to 0 is our asymptote, and we don't have any negative values we have a picture for. So what that would tell us is that if you want the domain of this function, you can set up the inequality that 16 minus x squared needs to be greater than 0. And if you factor that to get 4 plus x times 4 minus x, you know how to solve inequalities like that. And you can solve them with a sign diagram. So the zeros are going to be at 4 and negative 4. So I'm at 0 at both these locations. When I plug in a number that's a little bit less than negative 4, say negative 5, I'll see that this factorization is going to be negative. When I plug in a number between negative 4 and 4, say I plugged in 0, I get a positive value. And then when I plug in something bigger than 4, maybe 5, you're going to get a negative number again. So this would tell me that the domain of our function is going to be, so our domain is going to be negative 4 to 4, non-inclusive, because I know I can't plug the value of 0 into my logarithm. So I hope this video helps you, and the more you work with logarithms, the more you're going to get comfortable with them. But really make sure you understand how the logarithm relates to the exponential function. And to begin with that, I'd really dig in on understanding the graphs, and then you can work more towards understanding the algebra. So hope this video helped you. Smash the like button if it did, and have an awesome day.